Hi everyone. This is a project presentation of a course called Magnetic Resonance Imaging. In this particular project, our aim is to look at NMR from a physics standpoint through spin simulations. Our project consists of two parts. In the first part, we will compare quantum and classical spin in terms of their resonance behaviors, while in the second part, we deduce some information about relaxation parameters T1, T2 through spin simulations. In the most of the applications, we consider proton excitation process as a simple delta function, where at resonance frequency we have total absorption and at other frequency we have no absorption at all. However, this is not the case in reality, as you can see from experimental data. Knowing this process provides us with following informations like bandwidth, Q factor of the resonance, theoretical minimum slice thickness, and RF pulse period and amplitude designed for the maximum absorption. For this, we invoke Schrödinger equation with a simple Hamiltonian. It has a main field part and a time-dependent sinusoidal excitation part. We are numerically solving this complex valued equation using a fixed step size fourth-order Runge-Kutta for a total spin-up initial condition and look for the probability of spin-downs. This problem can also be solved analytically by time-dependent perturbation theory for small excitations. The results are of this form. You can see probability for the spin-up, spin-down state versus driving frequency for three different RF excitation durations. As the duration increases, the bandwidth of the resonance decreases. At B0, 1 Tesla, for example, an RF pulse amplitude of 10 microtesla, duration of 1 millisecond, we found the bandwidth of the resonance frequency as 37 Hz. This gives us a Q factor greater than 10 to the 6, and for a fixed 10 microtesla RF amplitude, theoretical minimum slide thickness is around 1 micrometer. Currently, MR machines have sub-millimeter resolution, therefore the limitation is on the instrumentation. For the second part, we have performed spin simulations. These are actually classical simulations to get a qualitative information for the spin parameters T1 and T2. To determine T1, we have performed an algorithm called Metropolis algorithm, and to determine T2, we have performed two simulations regarding random inhomogeneities and dipole-dipole interactions. Metropolis algorithm starts with a configuration of spins and change one of them at each iteration considering the probability given by partition function and Boltzmann distribution. Here you can observe for two different temperature spins are relaxed or randomized due to the temperature, where black squares represent spin up and whites are spin down. You can already tell for the low temperature relaxation is much slower. Our results are as follows. Relaxation time T1 is proportional to temperature. Formation of magnetization islands indicate presence of strongly magnetic ions, which can alter T1. For the second case, we are considering an animation where X projection of the spins represented by a color between black and white. If no dephasing occurs, we should see something like this. However, let us introduce a random inhomogeneity in the lattice. And these are the results of the total magnetization decays as a function of iteration step. These three graphs correspond to the three different standard deviations of the fluctuations increasing to the right. Therefore, we can say that D2 relaxation due to the random inhomogeneities decreases with increasing standard deviation of the fluctuation. Also, there are some secondary peaks are formed. Now consider a nearest neighbor dipole interaction. Notice how dephasing starts from the boundaries and propagate to the inside. This is because boundaries are unmatched and inside exhibits a greater symmetry. Therefore, they dephase later. Again, you can see three graphs corresponding to increasing strength of dipole interactions. As we can say, with the increasing interaction constant, T2 due to this mechanism decreases. We can also say secondary peaks are more suppressed as a function of time compared to the random fluctuations. We now summarize our findings as follows. Dipole relaxation is harder to recover due to the more suppressed secondary peaks. Random inhomogeneity relaxation is independent of the lattice size, whereas dipole relaxation depends on the lattice size. In the case of random inhomogeneity, T2 relaxation time is inversely proportional to the standard deviation of the random fluctuation amplitude. And for dipole relaxation, T2 is strongly depends on dipole strength. Finally, we have a challenge question. How would MRI be with higher spins like 1 and 3.5, where you have more than 2 spin states? It's hard to imagine. Thanks for listening.